Hi everyone, let's talk about solving the Lucas linear recurrence. We have this sequence of numbers where the first number, the zeroth number, is 2, L1 is 1, and for all numbers in the sequence after that, so L2 and beyond, Ln is equal to Ln minus 1 plus Ln minus 2. So the first few numbers of the sequence are 2, 1, 3, 4, 7, 11, 18, 29, 47, and so on. Now it's natural to ask whether ln can be written as a function, so like a closed form function. So let's say h of n. So h is a function and we apply it to the number n and we get ln. So we're gonna work on finding a formula like that using the theory of linear recurrences. The first thing is that we need to find the characteristic polynomial. Characteristic polynomial. That characteristic polynomial in this case, since we have this recurrence, it's going to be a quadratic and it equals x squared is equal to x plus 1. So that's the equation, but the actual polynomial is just x squared minus x minus 1. And we're going to let that equal to f of x. Next, what we have to do is find the roots of the characteristic polynomial. So the roots by the quadratic formula are phi, which is equal to 1 plus square root of 5 over 2. That's the golden ratio. And c, which is equal to 1 minus square root of 5 over 2. That's the radical conjugate of the golden ratio. Notice that these are not equal to each other, so they're distinct. And that is what is going to allow us to use one of the easier cases of the theory of linear recurrences. What that theory tells us is that since the roots are distinct, there exists c1 and c2 in the real numbers, such that for all n that is greater than or equal to 0 integers, it holds that ln is equal to c1 phi to the n plus c2 c to the n. So we just have to find out what this c1 and c2 are, and we're home free. What we'll do is that we'll use L0 and L1 because L0 is equal to 2 and L1 is equal to 1. So we know that by the recurrence this is just c1 plus c2 using this recurrence, and this is equal to c1 phi plus c2 c. So now it's just a matter of solving for c1 and c2. What we find from the first equation is that c2 is equal to 2 minus c1. And then according to the second equation, by plugging it in, we find that 1 equals to c1 phi plus 2 minus c1 c, which is equal to c1 phi minus 2c, plus 2c minus c1c. And that's equal to c1 phi minus c plus 2c. And that allows us to isolate c1 as 1 minus 2c divided by phi minus c. So we just have to compute that out now. So let's recall the definition of c and phi. This is phi, the golden ratio, and this is c, the radical conjugate of the golden ratio. So if we plug those in, we find that c1 is equal to 1 minus square root of 5 divided by square root of 5, and that's just equal to 1. And c2 is equal to 2 minus c1, which is 2 minus 1, that's also equal to 1. So c1 equals to c2 equals to 1, and according to the theory of linear recurrences, we can just write that ln is equal to phi to the n plus c to the n. So that's equal to 1 plus square root of 5 over 2 to the n plus 1 minus square root of 5 over 2 to the n. And I know this doesn't even look like it outputs integers, but there is enough cancellations that it does always output an integer for non-negative integers n. Thanks for watching, and I'll see you next time.